Okay, anyways, let's dive into this. Let's find. I don't want to hear him. Don't tell him I'm talking shit about him. He's way bigger than me.
Make sure that's not on the recording.
Yeah, I know, yeah. You're right. It is the first 3 seconds of the recording. I'm making fun of him. Axel, will you hit the light, the one on this side, closest to me? There we go. All right, so let's finally 9 minutes into class. Let's begin lecture. Actually, I covered Canvas. So there, I did it. All right, so that's the concept of pre-stressed concrete. It is these guys. I took this stuff right out of Stanton's notes. These are just some concepts that are worth discussing a bit. So pre-stressing has been around a long time in different capacities. That one good example of that is a bow saw. Right, so if I'm pushing on this bow saw from this direction, right, this half of the bow will be in tension, right, because this is coming around and it's pulling on that, and so this part will be in tension, but this side over here is going to be in compression, right? And is that going to be a problem when you're sawing something? Yeah, what's going to happen on this side? It's going to buckle, right? Because you push it. Your bow saw is very thin, has very flexible. You push that direction, it's going to buckle. So this isn't going to do us any good if that's buckled on that side. So what we do is we pre-tension this, right? So we just apply, right? There's like on the end of these things, there's a little screw that you twist up, and then when it does, it applies tension to this. So that thing is pre-tensioned before we start. So if we take tension on this side, compression on this side, add on to it a bunch of pre-tensioning with that little screw there that pre-tensions this. So when you push on it, the combined effect, well, everything remains in tension. This side goes into more tension, and this side goes into less tension, right? It was at this tension, but we add on the compression, it becomes less tension. And that's great because now this side won't buckle, right? So that's an area that maybe in your real world you have actually seen and used some pre-tensioning, right? Another example would be a bike wheel, right? A bike wheel, right? You've seen spokes on a bike wheel. They're very, very thin. And so when this thing rolls around and you have weight on there, this spoke right here would go into compression and that would buckle, right? It would buckle if I was doing that. But to counter that is we pre-tension all of our spokes. So this is it would go into compression down here on this end right here. But what we can do is we can pre-tension all those spokes. So again, via screwing, you could kind of screw each one of these spokes, we pre-tension, so everything is in a lot of tension. So then when you take this tension and this compression down at the end, we get a result that everything remains in tension, and so nothing buckles, right? So we add, so this is and then, this is the loads without it, this is the pre-tensioning, and the two added together, we end up with everything in tension. So that's another example of it. Another one, this came out of a book, this didn't come out of Stanton's notes, would be a barrel, right? A wooden barrel. I don't know how relevant wooden barrels are in today's society, right? Maybe at a whiskey plant, they still use wooden barrels, but this is a thing that they used to do, right? You have I actually honestly used to wonder about this a little bit, right? You have these wooden slats that you're putting next to each other, and when you put loads in there, it'll expand out and then it'll leak, right? And so to prevent that is they pre-tension these things. So that they are pre-compression, I guess. They pre-tension the steel and pre-compress all of the wood so that nothing ever goes into tension. It's all the wood is in compression on the outsides, and then when you apply the load on the inside, it will want to expand things, but it can't. It will still expand things, but since we pre-compressed it, then it won't ever go into tension. It'll stay in compression the entire time, right? And then therefore it doesn't leak, right? And so, obviously that's not what we do in engineering or in civil engineering or pre-stressed engineering. We do this with pre-stressing. We use pre-stressing in beams, right? And so this is a typical. This came out of Stanton's notes. This is just an example, a simplest example of how we analyze these. What up, Neil? Yeah, on the beginning of the video that I recorded, I'm making fun of a Neil, but it's not you. It's a different Neil, okay? Just that has practice right now. I made fun of you, then I pictured you, and then I felt bad.
You got scared.
What's that?
You got scared.
Yeah, I got scared, Gavin, is what happened. I got scared and I backed off, and then unfortunately I started the recording already, and so yeah. And so this is what we use it in, right? So we have a beam, right? And if and these things aren't labeled here, but this would be right, the stresses we would feel under external loading. Oh, not losing. Right, that's what this one is, right? Under regular external loading, due to these loads being applied, right, we're gonna get tension at the bottom and compression up at the top. Tension at the bottom, compression at the top. So tension here and compression up here, right? But, right, is concrete very good at carrying tension? No, right? What happens to it? Cracks, right? We don't want crack. It'd still be structurally stable. Cracks don't necessarily mean that things are failed, but crack, we typically don't like cracks in our structures, right? And so to prevent that, what we do is we add some sort of pre-tensioning in there, some sort of pre-compression, I guess is another way. We pre-tension the steel, but pre-compress the concrete. So we put the concrete in a bunch of compression to begin with by tensioning this steel that's right here. And that's what this is. So this is from the pre-stressing. So this one is. That's what that one is there, from the pre-stressing, right? And so then when you combine the two, right? When you combine the two, that's what's over here. Oh, that's what's over here on the right here is the combination. So when we apply this pre-tensioning or pre-compression with the external loads, what you get is, right, these things are additive. We get this compression plus this compression, so it gets bigger. And then on this end, we take the compression and the tension, and so we still have a little bit of compression. We want this compression to be bigger than this tension, so we end up with still compression. So when we apply this load, right, this is what we get. We get compression, more compression in the top and less compression at the bottom, but no tension anywhere, which is great. If we don't have any tension, that means no cracks, right? And that's the whole purpose of pre-stressing, which seems a little crazy, is that we're doing all of this, right? Like I said before, it doesn't necessarily, if a crack forms, regular reinforced concrete, everybody took concrete or structures too, right? We just assume, it cracks at the bottom. And then it cracks up until where A is at, where the depth is at, and then we just assume that it cracks up to there. And then we never said it failed, right? It's still fine. It just has a crack in there, and we don't want the crack. And you can make it structurally stable. Nobody's going to die. Everything's totally fine. There's cracks all over the place, but who cares? Nobody dies. All of pre-stressing concrete is just to prevent those cracks from happening. It is a serviceability thing, right? It's not a life or death thing. It's just I just don't want cracks in it. I just don't want cracks in it. That's literally what it is. I don't want cracks. Right? Sure, that can lead to something, right? The cracks would then provide an avenue for chlorides to get in and start deteriorating stuff. The cracks, like I said, with serviceability stuff, nobody dies. Nobody dies. No, right? But it can lead to that, lead to that stuff. But it's very strange that, like in pre-stressed concrete, when we do this design, we start out with a serviceability condition, and then we check to see if it's okay and people are going to die or not, which is the opposite of the way we usually do things, right? Usually we say, are people going to die, right? Great, nobody's going to die. How about the deflections, right, and the after effect? Pre-stressed concrete's the other way. It's like, oh, let's make sure, is it going to crack? I don't want it to crack. It's not going to crack? Great. Now are people going to die? Oh, people are going to die. And then you move on. That's literally what it is. So that's a little strange. But then this is it. What you see for the mechanics right here, those are the mechanics, right? So if I know there's force P coming in right there, right? There's a big force P, a force pressure coming from the pre-stressed concrete, right? If I have a big force coming in, I can calculate that force on either end. What are these stresses? P over A. That's it. P over A. How about these stresses? If I have this load on the outside and I have this beam being loaded, what are these stresses? No. We're going, this is elastic. Everything's just elastic, right? Because that's a good point. We're not going nonlinear. That's the other thing. We're serviceability. Everything's still linear. Materials are still in the linear range, right? What are the stresses in a beam? Oh, this is... I keep looking at you, Gavin. You're right in front.
Yeah, why are you looking at me?
I don't know. You look smarter than everybody else with your glasses. Yeah. Tony, that's right. My over I. Right? You were just going to say, or M over S. I was thinking M over S. Yeah. But my over I. That's it. Okay? P over A. P over A. My over I. That's it. Those are the equations. You do, so like to calculate these stresses up here at the top, like these total stresses, we do P over A plus My over I. And then you come down here, P over A plus My over I. Gotta be careful of signs. We'll come up with a sign convention later on. Like tension's gonna be positive, compression's gonna be negative, and we're gonna deal with that. But that's it. When we derive the equation in a while, that's the equation. We already derived it. My, where it gets difficult, and we'll talk about this in a few minutes, is the loading stages. When we cast this beam, right at the beginning, the concrete's one strength, and we pre-stress it, it's one strength, right? But then after some time, the concrete gains strength. There's a thing called pre-stress losses. As things start moving around, we lose some of our pre-stressing forces, and that changes, right? The loads on it change. Sometimes under construction, certain loads are on and other loads are on. So it does get calm. If you're like, well, this is too easy of a class, just wait. Things get very difficult because we have to consider all these different load stages as we go through there, right? And because all these things are changing throughout. But really, just the mechanics itself, very simple. Very simple. Okay, brief history. My history that I had used in years past is very brief. ChatGPT has had this. All had this someplace. I asked ChatGPT to make this for me as well. Okay, I had all the key names in my early stuff, but this is actually use in concrete is actually very new. Okay. I think especially in the United States, right? So the first ones, it's interesting, it went all the way to 1872 and 1888, right? There's these ones, and they're like, hey, I have an idea for concrete, this pre-stressed concrete, and that was it, right? That's as far as it went. They didn't have the materials, they didn't have the materials, right? Or the ability to actually do anything with it, but it was an idea that these two people had, okay? Birth of modern pre-stressing. This guy is known as like the godfather, considered the father of pre-stressed concrete. You know, I kind of wish that. I kind of feel like I've missed out. Like I need to come up with a father of something in terms of my career.
Kids.
Well, that's true, Gavin. I am the father of my kids. I think as far as the younger one looked just like the older one, looks more like the neighbor. I'm not. The other one. So good point, Gavin. But I do feel like career-wise, I've missed out on the father of something. I got to come up with something. Yeah, fly ash and glass concrete. I could maybe be I did that, but nobody uses it or anything. But someday, maybe I'll be famous. Right, so he did some important stuff early on, right? The one thing we're going to learn a little bit later is that you need special materials for this. You can't get away with like regular steel and regular concrete. Regular concrete's fine. Regular steel though is the problem, right? Because of these things where we pre-stress losses that we're going to get in before. If the concrete moves a little bit, then you lose a lot of your pre-stressing, right? So conventional. Might as well talk about this. Conventional steel. What's conventional steel in terms of its KSI, like its ultimate capacity?
60?
Yeah, 60 KSI, 50 KSI, somewhere in that range. Any guesses on what pre-stressing steel is at?
90?
270. Yeah. 270 KSI. It's special material, right? Because of the pre-stress losses. That alone, that idea alone, even just steel alone, right? Just regular steel, 50 KSI, right? 1 square inch, 50,000 fucking pounds, 50,000 pounds. Right? A typical car is about 5,000 pounds. So 10 cars could hang from one. That fucked up, right? Isn't that just like that is like, I mean, really, that's kind of magical that we can make stuff like that, right? But then 270,000 pounds per square inch, right? That's the material is. So some of these guys, they had some ideas, but they didn't have the materials to back it up, right? And to make it work. And so these guys, when it actually started happening was with this Freyssinet, right? And then he actually started using it and stuff like that. And the other important name to see in here is Magnell, this guy. Gustav Megnell. It's probably not how you say his name. But he introduced the pre-stressing in the United States after World War II. And so that's where it first started getting used. So the very first use of it was the Walnut Lane Bridge in 1950. So if the oldest pre-stressing in the United States was from 1950, just to show you like that's how new this material is to the United States. And you know, it's interesting. It's like, and that bridge still exists. I kind of hope it still exists, right? It's only 50, it's 75 years old. I guess that's getting up there, right? The typical design life in Astro, which we'll talk about later, I think it's a 75-year design life on a typical bridge. We've designed them to last for 75 years. So, but anyways, it's still used today. You can go, maybe when you're out in Philadelphia, you could go over to the first Walnut Street Bridge and be like, look at this. I bet there's got to be some sort of monument there for this. Right. And then the other thing that's becoming more prevalent nowadays, especially, and we'll talk about the difference between pre-stressing or pre-tensioning and post-tensioning in a minute, but post-tensioning is becoming more and more prevalent now. And in fact, it's just in the last like 10 years starting to be used in commercial and residential construction quite a bit because of the advantages we're talking about. Okay, mainly just no cracking, right, and being able to get longer spans with cracking and deflections are improved. Okay. Right, so then, anyways, that's the rest of it. I'll post this on our Canvas page so you can kind of read what ChatGPT has to say about it. But then one thing I always like to do, I pulled this right out of the text, right, or a textbook that I had, what pre-stressed concrete is, right, how it works and stuff like that. And then I said, this is just for fun here, I said, can you give this to me in Gen Z slang? Right, that's one thing I always like to do. It actually, one thing I was talking to, I did this in Dynamics this morning too. One thing what's interesting about it is that it actually is really good at explaining it, and like it doesn't lose its concept. It still has its own concept. It's just using Gen Z slang. Concrete is like when you pre-game before an actual game. It's concrete that's been pre-boosted so it can handle more stress. Concrete is boss, squeezing compression, but kind of weak when pulled. Tension. By giving a pre-boost, you can handle the pull vibes better, right? Imagine pulling a rubber band super tight, then gluing it down, letting the glue dry. Once it's dry, then it's interesting. Okay, this is another one. This is Abraham Lincoln. I was like, could you describe my fellow countrymen in March of Progress, just our great nation finds strength and unity. So I mean, look at it, brings in the strength and unity thing, right? Like, whew, right? So too will discover advancements in the realm of construction. Behold the marvel of pre-stressed concrete. Right? Let's see if you guess this one.
Trump.
This Donald. First off, let me tell you, it's the best concrete. Everybody says so.
You got too much time.
Yeah. The good news is it only takes a couple seconds, right? It's just like
Still too much.
We take steel. We take the steel, the best steel, American steel. We pull it right. That's pretty good. The other thing, well, more time here, Connor. Like I said, make me a rap. I said make me a rap. But what's interesting, and I need to do this, and I don't think I did. There is a web, and I didn't have the time this morning, but you can take this and you can put it into an AI generator and it'll sing it. It'll actually sing it. So next time, if I have the time, Connor, I'm going to put together the rap where it's being sung by AI as well. And it actually is pretty good. I did instructions one last semester on different lateral systems. It was on the different lateral systems that you find in a building. You're right, Connor. You're absolutely right. I have it's too much time. Okay. I gotta get my notes out. I've been winging it so far. I keep my notes on here, and I'm not just texting. Sometimes I might be texting. Like earlier when I texted Tim. Has anybody designed or messed around with pre-stressed concrete in your real job? Yeah. A little bit? Very tiny bit, okay. Like you said, and just like anything, there are programs out there that do this analysis. But again, I think it's super important to understand what's happening so that you know how to use these programs correctly. All right, almost there. Okay, and we already, I touched on this a little bit before on what these pre-stress losses were, but. That's what, when we're referring to these things, we lose tension, right? And these things we lose tension in the steel, which amounts to tension in steel, we'll say, which amounts to loss of compression. And this is one of those things that make things more complicated because we have to take this into consideration, right? So this is 35 to 60 KSI. Kids. KSI and losses, right? So need very strong steel, right? If we're going to lose 35 to 60 KSI in pre-stress losses, we have to start out with way higher than that, right? Where do we get that from? Well, there's elastic losses, right? We'll cover that in a little bit, but like when you don't get them in post-tension, but you get it in pre-stressing, we'll get these elastic losses. Just when you transfer the load from the steel into the concrete deforms, right? Like it starts out here, it's been stretched, and then you transfer it into the steel. When you transfer from the steel into the concrete squishes. And when the concrete squishes, the steel gets stretched less, and so you lose some of those. That's what these elastic losses are. We also get creep losses. That's a big component, right? Concrete has a tendency to lose its resistance to continued load, right? You've learned it. So if you just push on concrete, you just over time under the same load, it'll just slowly move. It's kind of like a glacial flow is how I think about it. And honestly, it is a flow that's happening when it does do the creeping. Because if you want to get less creeps, you put less creeping. You put more coarse aggregate in there. The rocks don't creep. It's the paste and everything around the outside. A perfect example of creeping is the corners of Cobley Hall. Right? If you right out here, if you look, there's the corners, there's no like support, it's cantilevered out and it goes all the way up. Oh, this is a perfect example. And you can see that the corner is just over time, over the last 75 years, it is deflecting down. And in fact, it's causing major issues because vertically there's cracks that form because of all that creeping up the side. Look out the window there. Look out there. Yeah. You see these cracks that are happening all the way.
You see the slab sag.
You see those cracks that they tried filling them in up above that window up there? It's because this corner down here is sagging and it's causing that. And then one thing that they're doing, they cut off all the eyebrows out here, but they also put that vertical cut. See that vertical cut through all the brick? And that's to prevent like the brick from cracking and do that.
Just pretend you're
Yeah.
That's what I'm thinking.
You can just use your imagination and what it looks like. Yeah, but it's pretty interesting. So that's creep. Creep will cause it, right? So you pre-stress your steel and then you transfer it to the concrete. The concrete creeps a little bit. We lose the elastic stuff, but then over time it just sits there, and over time it just continues to squish like this, and then the steel becomes less stretched. And if the steel is less stretched, then your forces go down. So we're going to get pre-stress losses due to creep, right? And there's also steel has something similar. It's called relaxation in steel, right? So we have these steel cables that are being pulled, and then just over time under that sustained load, they start relaxing a little bit and they start applying less of a force as time goes on, right?
So it's like fatigue.
Kind of, but not. Fatigue has to do with repeated loads, right? Repeated loads over and over. Did you ask that, Connor? Yeah, okay. It repeated loads. It's over and over and over of squishing and tension. This is more just under sustained load. It just relaxes and just kind of stretches out a little bit. And then the forces go down due to that, right? So that exists, right? And so that's one of the things that complicates things tremendously. Okay, so the materials that are used in this, right? Steel. Like I give you some foreshadowing there. We actually want, do you think you want our steel to be stiff or flexible?
Stiff.
Wrong.
Flexible.
Yes. What's that? Yeah, you want it to be flexible. Good job, Gavin. See, I told you this as far as one idea, right? Right? So then the reason for that, right? If it's stiff, means that it gains load really fast under small deflections. Well, the opposite happens too. If there's a small deflection, you're going to lose lots of load quickly too, right? We want the opposite of that. We want something flexible. So a large change in deflection will cause less of a change in force, or vice versa. A large change in deflection will cause less of a reduction in force, right? So we want flexible steel. Turns out you can't do it. You kind of do it just a little bit. Instead of doing, we'll talk about this. Instead of doing 29,000 KSI, 29,000 KSI for your elastic modulus, it's 28,500. So it's just, it's just not much more flexible. But theoretically, if you can get something that's very flexible, is what you want. Okay, we want high strength. Right, because of large pre-stress losses. We want it ductile. We always want stuff ductile. We don't want brittle failures. Did I skip pages? Did I skip a page? I did. God, there's all this shit that I forgot to talk about. It's because I skipped the thing. Let's finish this. I'll go back to that. Gavin, you're in charge of keeping me on track here. We want it. Yeah, good point. Resistance. We want fatigue resistance. We want to have good fatigue resistance. Right. We want good bond. This is where we jumped so far ahead. We skipped a page, right, between concrete and steel. Right, because at some point, well, it depends, right, for pre-tensioning. It's like all these things I didn't talk about, and I didn't understand where it was. All right. Low relaxation. Yeah. Those are all the concepts we want to make sure that our steel's out. I'm going to come back. Once you finish writing that, I'm going to flip back to what I skipped. Oh, we skipped everything, right? Because I'd said history, and then we went on. Right. I got really excited, Connor. Oh, look at this. Whew. Okay, so there's a good point. I was like, God, I swear, I wasn't finished yet. Connor, I actually forgot about that, and I'm really glad you reminded me. I wasn't finished. Wait a second. Yeah, I'm a doctor. That's the other thing I forgot about. That's great. Okay, so there's two types of pre-stressing. We use these things interchangeably. Or at least I do, right? I don't know if people in industry does, but I'm pretty sure it does. We just call it all pre-stressing, right? So there's pre-tensioning and post-tensioning. Pre-tensioning happens in precast. They have to be precast in order for this to happen. And what we do, and the reason it has to be precast is in order for this to work, you have to have big abutments. So you have these big concrete abutments on either end. And what you do is between those two big abutments, we stretch steel, right? So we're gonna have some steel that spans across this, right? Right? And what we do is we pull on this, right? And then we stretch it. We stretch that steel, right? And the reason you need an abutment on either end is on this end, you have to be holding it steady. And then on this end, you have to push off of something so that you can pull it, right? So there's literally there's a jack that goes like this, right? That spans around, and then you have to, and that jack is you're pushing against the concrete, right? You're pushing against the concrete this way while you're pulling this way, and so you pull and you stretch that stretch that steel. So steel's all stretched out, and then once that's stretched out, it's scary as hell. There's a pre-stress plant in Billings, and in the past we've toured it. Maybe we could do it. Maybe we could tour it. You go there, it's pretty cool. And then there's the steel that's stretched out. So it's 270 KSI steel per square inch, right? And you're stressing this stuff to like 240 KSI, so they're almost 270. That's per square inch. Do you think they use more than 1 square inch? Absolutely, right? So they're dealing with like millions and millions of pounds of force that they're applying to the steel, and it's all stretched out. And sometimes they do this even with it. They hold it down. They hold it down here and here, right? So it's going down like this, and then it goes across, and then it goes up like this. And so so you're pulling, millions of pounds that way, and you have these hold down points, right? You imagine one of those hold down points fails, right? And that thing shoots up. There's a Mythbusters on this about if it would cut your head off and stuff. Pretty sure it would. Pretty sure. They actually try to avoid that because of the dangers of like putting that kind of forces and these hold down forces that people are working around it and stuff. Okay, so steel's stretched, scary. Then what they do afterwards is they come in and they cast concrete. They say, all right, I'm going to put concrete around like this. Right? And they actually cast the concrete around the steel, and the steel bonds to it, right? So literally they just form it up all around it, pour concrete in there, right? And then it bonds to the steel, and it's all kind of attached to each other. And then you have to wait, right? You have to wait for the concrete to come to strength. When the concrete comes to strength, then what they do is they come in and they cut it after the fact. They come in and, let's see if I can draw a pair of scissors. Nailed it. Okay? They cut there, and then they cut here. Probably don't use scissors. Okay?
Probably.
Probably. Just, yeah. Got scissors in there. But after it's come to strength, they come in and they cut that, right? And then what happens when you cut that? Well, it transfers the load from these abutments into the concrete, right? Just releases it, and it goes, right? And when it does that, it pulls the concrete with it, right? Because it's bonded, right? Like I said before, sometimes you want it bonded. You want it bonded in pre-tensioning, right? Because you pre-tensioned it, you cast the concrete, you release it, right? And then that steel was like, well, I'm going to go back to my original shape, and it squishes up. And when it squishes up, it also brings the concrete with it, and then it does that. Okay, that's pre-tensioning. That only can happen at a concrete, like a precast plant. And so then once you have that, then it's done, right? What the benefit of doing pre-tensioning is you can't get corrosion or anything in there, right? Because it's sealed to the concrete. The concrete's covering all of it, and it's good to go. Okay. Right? And you do it in a plant, and so all the dangerous stuff happens like in a factory, basically. And so you're not doing anything dangerous in the field, right? Post-tensioning is different, right? You do it, as the name implies, you do the tensioning after the fact, right? So in this case, right, what we do is we have our concrete that's been cast in the field, and my concrete beams cast in the field, and then what I do is I put a duct in it. Now, this is in its simplest form. There's other ways of doing it. We'll talk about it in a second, right? So there's basically a hollow duct in the middle of it. Okay, make sure I emphasize the T in there. It's not ducts. Just in case you were wondering, it's not ducts in it. It was ducts with a T. I always make sure I say that in when you're talking about tape too. When people think you're going around saying duct tape, it's duct tape. Although there's a brand of duct tape that's called duct tape. Do you guys aware of this? No. Besides the point. Okay, so we've cast this, and so this what's nice about this is you could do this in the field. You don't have to pre-order it. In the field, we've come in, you cast the concrete with the duct, or really what they do, like this is actually how they do in some bridge elements, but in floor systems, what they do is they have steel cables that have like a sheathing around the outside of it, right? So it's like a plastic sheathing, which is kind of like a duct that travels around with the steel. And you lay that stuff down. And so it has a sheathing, and it has like grease and stuff inside the sheathing. And then it's not going to bond to the concrete. The point is it's not going to bond, that steel isn't going to bond to the concrete. And then you cast that in the concrete, which is essentially a duct that's going through it. And then what you do is you have your steel that goes through it, through that duct, right? And it's not bonded to it. So you've cast the concrete, it's come to strength, and then I have the steel that's going through it. Well, what I do is on this end, right, there's a dead end and a live end. On one of the ends, right, we put an anchor of some sort, right? So on the dead end, I put an anchor. And then on the live end, I do what we did before in the other system, is I have a jack. I have a jack that then, God dang it, could do that. There we go. That I then pull on the end of the steel, and I push against the concrete. So there's no ducts that are required. Or there's no abutments that are required. I just sitting in place. I anchor one end. I make that the dead end. I go over to the live end. I grab the end of that steel and I pull on it. While I'm pulling on it, I'm pushing against. Right. I'm pushing against my my concrete, and I'm transferring some load in there. And then once I get it up to the load that I want, then I come in and I put another anchor on this end. Right? I put another anchor on that end once it's stressed, and then boom, I got a pre-stressed beam, or a pre-stressed beam, but a post-tension beam. Okay? And so you can see that there's a big difference, right? Up here, right, pre-tensioned beams, the load from the steel is transferred to the concrete along its entire length, right? Along this entire length is transferring it because it's bonded to the concrete. Over here, right, the way you're transferring the load from the steel into the concrete is a big-ass point load right here and a big-ass point load right here. Just two big-ass point loads, right? This one scares me. It's not bonded, right? It's not bonded at all. This one always scares me because, like, what if this anchor failed? Right? What if that anchor failed? Pew, pew. Right? It's not. There's nothing holding it in there, right? Pew, shoots out the other end. Or, not the anchor failed. What if the steel fails? What if you break the steel as you're pulling the load, and then ship flies out the end, right? And that does happen, right? So when you're on a job site and they're doing post-tensioning, don't put your head right here. Right? Don't come over there, just put your head down there, right? Millions of pounds of force being released like instantaneously, right? That I think an old homework, I had the students calculate what velocity that steel would shoot out the end at, right? Using work energy, right? The 1/2 ks squared, equal 1/2 mv squared, right? You can calculate what the energy or the velocity of the steel shooting out the end. And it, like I said, it does indeed happen where it breaks like that.
Grout the duct after.
So sometimes that's a good point. Sometimes they do that. Sometimes they're like, okay, now I don't like, because what else can happen, right? Is like you alluded to, right? Stuff can get in there, right? Water and air and get corrosion, and then that gets in and it corrodes these post-tensioning tendons, which is bad. So a lot of times, sometimes what they'll do is they'll come in and they'll pump grout through it, and they pump grout through it. Then we do have like a bonded system at that point, right? And it'll protect it. But really, I think usually what they do, again, they have the way that they do these floors is they just have cables that have the unbonded steel on the inside of it, and then they have it filled with grease and stuff, because also when you're pulling on it, you get all sorts of weird because you can actually very common is we'll talk about it later, but it won't just be straight across. It'll actually have a shape to it. What you're trying to cancel out is the external moments, right? You try to cancel out. So you're ideally, if you shape your steel on the inside the same shape as your moment diagram, like kind of reversed, you can cancel those things out. So oftentimes they do that with it, and you get all these friction losses because you're pulling on it. You're trying to pull steel around a corner, and you get these friction losses. So they put grease in there to help with those friction losses as they're pulling around that corner. And then also that steel or the grease acts to protect it from corrosion. But they have really fancy anchors that just prevent like egress, movement of water into the steel. That's a good point. That's a big part of it. Later on in the semester, I'll show you a presentation of a building in Seattle that had that problem. They didn't properly anchor the ends of it, and the building was less than 10 years old. It was like a 14-story building that they tore down the whole thing because water got into the thing and started corroding things. And then the residents would be in there and they'd be like sleeping. And then what would happen is these tendons break. Right? Would you think that makes a noise? Right? Yeah, so you'd be sleeping and all of a sudden you're like, what the fuck was that? And it was just the tendons. Don't worry, it's just serviceability. Just, right? It's just like, oh shit. And then it turns out like, I have a friend that does forensics, and they came up with a plan to save the building, and then ultimately they lost because people were just like, we don't. And what it was is they put in an acoustic monitoring system to listen for cables breaking, and so when they did their solution, like fixed it and prevented air from getting in there and water from getting in there, they could see how the tendon breaks started out up here, and then they decreased to nothing, and they're like, see, it's all better. but no, right? Like, I'm not, like, how many broke before you put that system in, right? Like, I don't know. Anyways, we'll talk about that later. Okay. Why would you do this, right? We've hinted towards this. What are we doing? Oh, we're out of time. What we'll do next time is we'll start talking about the pros and cons of doing this, right? Why did we do it? We talked about it before. Mainly it's for serviceability. We don't like cracks, right? And it'll increase the lifespan of the structure and things like that. The cons are it's expensive, right? It's old concrete, just cast it and let it sit there forever. And this now you got to do all sorts of shit to it. So it's just expensive. But we'll get into that. All right, great.